Okay. So yesterday we have started with folding, where basically we would go for a area optimization with the help of the folding. So where you can reuse the function by n number of times with the penalty of increasing the computational time n. So we have gone through this particular example where we have seen that how we can actually apply the basic concept of folding. So ultimately we need to use some sort of switching instances, because we need to change the position of the switch accordingly whatever our functionality we want to achieve. Then we have seen about this folding transformation, and we talk about this particular equation. So yesterday we talk about this particular equation where how we can derive it. Okay. So that is when we go from U to V. So at that time PU, that is a parallel stage of U, is very important. Okay. So that is there in your equation. Now whenever you go for any folding architecture, actually this example we will not see it right now, but just to understand that how we can solve the folding example. So suppose that this is your original circuit which is given. This is your original circuit. Okay. Now if you observe over here, here you have a 4 adder and you have a 4 multiplier. Okay. Now if we want to apply a folding, then what we can do that ultimately if I apply a folding where I consider I would like to do with 1 adder and 2 multiplier, sorry, 1 multiplier, then ultimately if we want to achieve this functionality, then we need to fold it 4 number of times. So your folding factor n would be 4, because with the 1 adder you want to you want to achieve the functionality which is equivalent to 4 adder. Okay. So ultimately in order to save our area, we would like to use a 1 adder and 1 multiplier instead of 4 adder 4 multiplier, and this 1 adder and 1 multiplier we will run it 4 number of times, and this way you can get it. Now so this is actually a structure. Currently, we are not actually interested to see this because we need to see this later on. Okay. But what is important that what is given? The folding factor n is given. Now folding factor n is given. So that means you need to replace 4 adder with the 1 adder. Okay. Then I can apply the folding factor 4. So ultimately 1 adder and 1 multiplier is given. Apart from that, you have a folding set. Now folding set is defining a order in which the folding or the execution would happen. Okay. So S1 is related to the add operation, S2 is related to multiply operation. And since we are folding it 4 times, so we need to actually take care of all 4 instances. Now if you observe this particular DFG, original DFG, and you observe that here first node notation of 1 is associated with the adder, similarly 2, 3 and 4. So 1, 2, 3, 4 are my adder, and 5, 6, 7, 8 are multiplier. So that means 1 to 4 are adder, 5 to 7 are 5 to 8 are multiplier. Now here in this particular example itself, the order is given. Now order, you just observed it. SL 0, Now what this you need to consider as a U. Okay, so this particular adder will assign an instance 4L plus 0. This you need to consider as a U value. Why 4? Because n is 4. So 4L plus 0 is there. Then this is 4L plus 1, that is a node 2. Node 3, it is nothing but 4L plus 3. And this is 4L plus, सॉरी 0, यहाँ पे 1 आएगा, ये 1 आएगा, सॉरी ये 1 आएगा, ये 2 आएगा. This is U ultimately. So sorry, this is 4L plus 3. Yes, this is 4L plus 2. Okay, so ensure that don't be confused like me. Like this is U. Okay, so this define your instance, and that will be reflected in your folding set. See over here, 4 is come first, so this you need to finally strictly follow the order. 4 come first, this comes second, third comes third, and 1 comes fourth. So this order, so that means 4L plus 1 will be executed, which is a node 1. Then this 4L plus 1 is associated with the node 2, so that's why second is 2. Then 4L plus 2 is associated with 3, so that means the third one, and then last is 1. Okay, so this is a folding order. Now why adder is means why this order is important? Because ultimately you have now a one adder only, and that one adder has to manage it. But now in order to preserve the functionality, you need to ensure a proper adder. Okay, if you don't follow the order properly, then the functionality would get changed. So ultimately whatever the node which is being associated, that node functionality has to be defined in a strictly one particular order, so that this original functionality should be preserved. So that's why this order is important. So first 4 has to be executed, 2, 3, 1. Okay, now whenever you want to solve the example, then this order is given to you. Okay, whenever you think about any for your application, then probably as you are developing the application, you know that what you want to achieve, and in order to achieve that, what should be the sequence of this particular operation, that you need to decide. Okay, but as far as the means our discussion is concerned, where in the book all the time this order is given to you. Okay, so they have identified that this way only strictly you need to follow. Similarly for S2, here you observe that. So this 5 comes first. So that is for a multiplier, 4L plus 0 instance is associated with 5. With the 8, 4L plus 1 instance is associated. With the 6, 4L plus 2 instance is associated. Okay, and 7, 4L plus 3. So you just observe that 5, whenever it is written, where is 5, 5? Here it is 0. Here it is 1. 8 is 1 instance. This is 2 and this is 3. So 5, 8, 6, 7. That is the order. 5, 8, 6, 7, which is being defined over here. Okay. Apart from this, another information is also given to you. That adder and multiplication requires 1 and 2 unit respectively. That means this particular resource, whatever the adder and multiplier, that resource will having a internal execution time is 1 unit and 2 unit. So multiplier is having a delay of 2 unit and adder is having a delay of 1 unit. And apart from that, the pipelining is also defined. One stage pipelining is for adder and two stage pipelining is for a multiplier. Now there may be a case that here this will be act as a see source 1 is a adder which act as a source. Here the 2 is act as a destination, while here you just observe 3 is a node which acts as a source because age is going from 3 to 1. Okay. Similarly, for the multiplier, you just observe that 5 to 3, where 5 is a multiplier, which is a source node, and 3 is a destination. So for the 5, which is the multiplier, you should know the pipelining. How many stage pipelining? Because Yesterday we just discussed that when we have a node and in between there is a edge connection, then we should know that what is the pipeline stage of my source node. So that will actually help us to define that at what time the execution of the destination node started. Okay. So this many information is given to you. You need to interpret it. Okay. So of course we will talk this in more details when we will solve the example. So currently I am not solving this, but this same example is there in a later part. Okay. Retiming is there. So retiming will ensure that whatever the equation that whatever we have derived it. Okay. So this equation is we have derived it. If you remember yesterday, this equation. Okay. So this equation has to give value greater than 0. Okay. Because all the parameter value you know. N is given. WE, that means once you have a DFG, you know that what is the weight associated with this age. V and U instance, that you can find it out with two way. Okay, this V and U instance and pipelining. So this all information is given to you. Now in this example, what we have discussed, this define nothing but the instance 4, 2, 3, 1. So that means 4L plus 0, 4L plus 1, 4L plus 2, 4L plus 3. So that instance is being defined as well as the number of stage of pipelining is also being defined. So this information is given to you, and with that you can find out the solution, that put all this value and find out that whether this value is greater than 0 or not. If this value any chance less than 0, then you need to apply the retime. Okay. So that detail we will think about this in later on when we will talk about the example in details. Now folding is also applicable for register minimization, because ultimately our objective is to we need to reduce our area. Now in order to reduce our area, the register which we use in between storage, okay, so that also we need to think about minimizing. So register minimization technique is also possible. Now for a register minimization, we need to understand some basic terminology. Okay, so that we are going to discuss, and then we will see the techniques through which we can go over a register minimization. So when I talk about the register minimization, then first of all you need to find out the lifetime analysis. What I mean by lifetime analysis? So lifetime analysis is a procedure which used to computate the minimum number of registers required to implement a DSP algorithm in hardware. Okay. So when we want to go for a register minimization technique, so first thing that we need to identify that for this particular functionality, or for this whatever we are going to optimize, for that how many minimum register that I need to use. So that means I need to find out first of all bare minimum register that is required in order to preserve the functionality of my original DFG. So that you need to find it out. So for that you need to go for a lifetime analysis. So lifetime analysis would help you to find out that what are the bare minimum number of register that is required to solve in order to preserve the functionality. So linear time analysis is also there, circular time life analysis is also there. Then in a lifetime analysis, the number of live variable at each time unit is computed, and the maximum number of variable at any point of time is determined. Okay. So what we used to do that we will find out the number of clock cycle, that this is the clock cycle. Now in this particular clock cycle, how many register I require in order to perform the particular functionality. So this I will repeat for all the clock cycle. Okay. So what I want to find it out, I need to find out the minimum number of registers. So for that we need to go for a lifetime analysis. In a lifetime analysis, what I need to do, I need to find out for a clock cycle number of live variable. Live variable, that means which number of register I require. Okay. So that I need to find out the requirement of a number of register for each clock cycle. for my execution. And from that, I need to identify the maximum number of maximum number of register at a one particular clock. Okay, so that give you idea that what are the bare minimum register that you require. Okay, so suppose that means my operation is running for a 10 clock. So maybe in a first clock I have a 2 register, second clock I have a 3 register, at a next clock I have a 4 register. Afterwards again you have a 3 2 3 2. So from 1 to 10, if you observe that, then there is a one particular clock which is a third clock where you require a 4 number of register. Okay. Apart from that, all the clock which has a lesser than 4 number of register. So that suggests that you need to actually use at least 4 register in order to complete the functionality. Okay. Now, as we require a register at a different. Hello. 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 Okay. So ultimately, whatever the maximum value of a register at a one particular clock, that would be the minimum amount of register that we require for our DFG. Okay. So that we need to find it out. So that also we will see with the example. And in order to go for a register minimization, there is a one very beautiful technique which are available, forward backward register allocation. Okay, so that we will see that how actually you can manage. Now you need to assign these 4 register. As I said that 1 to 10 clock cycle, you have observed that at a third clock cycle you require a 4 register, which is the maximum value from 1 to 10. So with that you require a 4 register. Now this 4 register, how you need to manage it for a different clock cycle. So for that this particular technique is there. So how you can use this 4 register for all the clock cycle. So that you can achieve it with the forward backward register. Now linear lifetime analysis. Okay. Now over here, the lifetime of a particular variable is given. Okay. So 3 variables are there: A, B and C. Okay. A having a life from, see, this is my first clock cycle, this is my second clock cycle, this is my third clock cycle, fourth clock cycle. So A is having a life from 1 to 4. Okay, what I mean by life means for that particular duration, the A is exist. Okay, what I mean by life of a particular variable, for this particular clock cycle, this particular variable do exist. So A is exist according to this particular graph 1 to 4. Okay, B is exist from 2 to 7. Okay, so B is exist from 2 to 7, and similarly the C is exist from 5 to 7. Okay, so this you can interpret from a graph, or if this is written in a word form that A is exist from 1 to 4, B is exist from 2 to 7 and C is exist to 5 to 7, then you can actually means draw this equivalent graph. Okay, so this is actually the linear time lifetime analysis. Okay, where we can draw like this. So it is a linear lifetime analysis where each variable, and for each variable the life of a variable for each particular time unit, it is being defined. Now I will count a number of active register or a number of active variable. This A, B, C you can talk as a variable, or maybe you can talk as a register, because ultimately in order to store this you require one register. So A, B, C, now I will find out of one particular clock cycle how many active registers are there. So here if you observe that A, B, C, so for A, B, C at 0 clock cycle, here it is 0. Okay, now for here if you observe 1 at one clock cycle, if you observe that there is a one variable which is active. So one first clock cycle is this period. First clock cycle is this period. So during this period, you observe that only A is active. So that's why I am writing 1 over here. B and C is absent. So that's why in a one clock cycle, in a first clock cycle, only one variable is active. Okay. Now think about this clock cycle, which is my second clock cycle. Okay. Now in a second clock cycle, if you observe, then this exists and this exists. So that means A and B exist, C doesn't exist. So that's why I will put two number over here. For this particular clock duration, I have a two variable exist. A and B exist, C is not exist. Similarly, I will go for a this. Again, A and B both are exist, so I am writing 2. Again for this duration, A and B exist, so that's why I am writing 2. For fifth clock cycle, B and C exist. Now A is absent, so you have a 2 number. Again for this particular duration, B and C exist. A is absent, so 2 require. And here also in a last clock cycle, B and C is that 2. So that means I have find out for each clock cycle what are number of variable active. So from this you just observe that this I have defined that in a first clock cycle 1. This is 0 because I am starting. Okay. So there is no active variable before this particular point. But afterwards, once the clock existence started, so at that time you will find out the number of active variable. Now you observe that 1, 2, 2, 2, 2, 2, 2 like this. So what is the maximum number of variable do exist at a particular time? So you just observe that कि आपका 2, 3, 4, 5, 6, 7 ये हर एक के लिए दो वैल्यू है. That I consider as a maximum. So that means I require a minimum number of variable or minimum number of register for this particular operation is 2. Okay. So for variable ABC, this is nothing but the active variable value. So 0, 1, 2, 2, 2. This is nothing but this value, whatever is being written. Okay. So this value is being replicated over here. So 0, 1, 2, 2, 2, out of which maximum number is 2. So that means for this particular example, I require a minimum number of register R2. Okay. Now it is being defined that n is equal to 6. Now n is equal to 6 is given. So n is equal to 6 is given. That means the folding factor is given 6. So that means ultimately whatever the activity that would happen inside my block, that is available from 6L plus 0 to 6L plus 5. So instant which could be associated with 6L plus 0 to 6L plus 5. This instance I consider as a first clock cycle, and this instance I consider as a sixth clock cycle. Okay. So first clock 6L plus 0, like at the last clock cycle 6L plus 5. Now I know ABC life. Okay. So let me just rub it again so that I know this ABC life. Okay. Now this ABC life is known to me. Now from this I will think about how I can draw this lifetime analysis graph. Now this actually we have seen it for a ABC. Now this actually iterative process. Okay, this whatever the graph that we have shown it, that is for single iteration. Okay, but this would be a iterative process. So that means it will run for a multiple loop. Okay, so now over there, how it can be managed? So for that, just consider that A0, A1, A2, B0, B1, B2. This is just 3 instances. That means I'm now expanding this, opening this for a 3 more loop. Okay, this A, B, C, I'm opening for 3 more loop. That means A0, B0, C0, which is for my first iteration, A1, B1, C1 is for my second iteration, and A3, B3 or A2, B2, C2 is for my third iteration. So now whenever A do exist, the life of A will not change. Okay, for any iteration, because we have already defined that life of A is from 1 to 4. So that means 1, 2, 3, 4, A0 exists. Okay. Then B0 exists. So I am still at a first iteration where B0 will execute it. So that B0 exists from this 2, 3, 4, 5, 6, 7. So that information is already here. Okay. And C exists is 5, 6, 7. So here also 5, 6, 7. So this is for C0. Okay. And this is for B0. So A0, B0, C0, that is for my first iteration. This is the graph. Now I am talking about the second iteration. Okay. Now for a second iteration, if I go, then for a second iteration, see, folding factor is 6. That means this particular activity will go for a 6 clock cycle, because it can have a 6L plus 0 to 6L plus 5 instance. As I define n is equal to 6, so always your NL plus U, where U will go from 0, 1 up to n minus 1. As I am starting with 0, I will go to n minus 1. Okay. So n is 6. So that means 0, 1, 2, 3, 4, 5. So this U value is 6L plus 0, 6L plus 1, 6L plus 2, likewise 6L plus 5. Now, this is for a second iteration. Now, after 6 clock cycle, again my next folding instance will start its execution. ठीक है, ये मेरा मान के चलो कि ये जो फर्स्ट है वो 6L plus 0 है, 6L plus 1, 6L plus 2, 3, 4, 5. Then again 6L plus 6 is nothing but the replica of 6L plus 0. Okay, so now again my A execution would start, because after this, once n is equal to 6 complete, then my next iteration start. Okay, because 6L plus 6 instance, that means 6L plus 0 to 6L plus 5 would be considered as the first iteration, and 6L plus 6 to 6L plus 11, if I am not wrong. That total again next 6 instance, but that is applicable for my another iteration. Okay, so that will be mapped to over here. Now if I consider A1, B1 and C1 for my next iteration, say again after 6 the execution of A start. So A will remain for active for 4 clock cycle, because it was active from 1 to 2. So from 6 again that U counter will be reset. Okay, so 1, 2, 3, 4. Then this B would start. If A start from this, then after 1 clock cycle the B would start. So that means B would start from here for second, third, 4, 5, 6, C1. And here what about C? 6 is for 5, 6, 7. So that is 5, 6, 7. Okay, so from this point onwards, again whatever is happen above, that mirror image would be there, but still the first iteration would be completed after 7. Means whatever has been started, that is still running, but for here the new A1 execution is started. See, B will not be started definitely. Okay, but here with this it is ensuring that B0 once complete, then the B1 start. B0, B1 cannot be started at the same time, because first of all the B0 has to be completed, then B1 has to be started. Then just see over here, B0 is started, then B1 is started is executed. So that is actually a good thing that B is utilizing always. Okay, that particular register is being utilized always. So This way, after 6, whatever is activity is happening from 0 to 6, okay, that you need to replicate for a 0 to 12 or 6 to 12. After 12, again, you just observe that this is for A3, that means third iteration. This is for A3. So again, 1, 2, 3, 4. This is for 2, 3, 4, 5, 6, 7. So this is probably for B3 and this is for C3. C3 is for 5, 6, 7. Okay. So this is keep on running for a number of iterations. So this way you can define it. Now again for this, when I consider n is equal to 6, then what will be the maximum value of live variable? So here you just observe 0, 1, 2, 2, 2, 2, 2. But at this particular instance, you require 3. Then 2, 2. So number of live variable that you are finding out, here it is 3. Now out of this, how many, what is the maximum value? Maximum value is actually 3. So that means if I consider n is equal to 6 and according to this lifetime of a ABC, I require maximum number or minimum number of register is 3. Okay. Yes. Any doubt? Okay. Now, I think this example maybe let me go to now register minimization technique for what we have seen. Okay. Now, see, now we have seen, just remember that lifetime of A. What is the lifetime of A? If we remember, A is 1, 2, 4. B is 2 to 7. And C is 5 to 7. This was the lifetime of A, B and C. And with n is equal to 6, what we have find it out? We have find it out minimum number of register was 3. Now that we will try to understand with the forward backward allocation. Okay. Now how this 3 register? So 3 register is required. So that I am defining R0, R1, R3. Sorry, R1, R2, R3. R1, R2, R3 is a minimum number of register that we have find it out over here. Just look at this again. So I am just keeping one example because actually in between there is a one example, another example, but I want to complete this for this example only for forward backward allocation. So just try to visualize this. Okay, 1 minute. I will maybe again. I need to charge my laptop. 1 minute. So minimum number of so minimum number of register which is actually being identified. Okay. So that minimum number of register which is being identified for n is equal to 6 for this example. That is 3. Minimum number of register is a maximum of live variable at a particular instance. Okay. Now with this we will try to see that how we can allocate this register. Okay. For that you need to first know this has to be given to you that A is active from first clock cycle to 4 clock cycle. Okay. Then B is 2 to 7 and This is 3 to 7. Okay. Now, if you observe that R1, you need to actually prepare one forward backward allocation table. So this is one table that you need to prepare. Okay. So this way you need to go for a register minimization. Okay. Now this 3 register I need to actually allocate for a different time interval. Okay. Now how I can do it? So that's what we want to see that. So ultimately life of C is up to 7. So that means I need to think about allocating this from 0 to 7. Okay. So here in this particular table you have a number of row and number of column. Now how the row is defined? The row is defined up to, for this ABC we need to go for allocation. So C has a life, so out of these 3, up to which particular clock cycle a variable life is exists. So that we need to think about. So that means that C is having a maximum value 7 for a clock cycle. So that means I need to draw this table up to 7. So that means number of row has to be start from 0 to 7. And first is a title of that particular row. So cycle, and after this I need to go up to 7. So 0 is your initial. So this is my first, second, third, fourth, 5, 6, 7. Okay. Now a life is exists from 1 to 4. Okay. So now this actually, this you need to understand that this is my first, combining this is my second. Okay. So now A is starting from initially and it will go up to 4. So if you observe that, see this 0 to 1, when I consider this, then this time instance is being defined. Actually slightly confusing over here. This is time instance 0, 1, 2, 3, 4, 5. So when I say this, then this particular time period is my first clock cycle. This is my first cycle. This is my second clock cycle. That you need to understand. Okay. So time instance 0 to 1, I have a 1 clock cycle. Time instance 1 to 2, I have a 2 clock cycle. So here just consider that I am talking about the time instance over here. So now 0 to 1, if you observe that only A exists. Okay, because A life is 1 to 4. So that means A exists, that A is, this is for time scale 1, 2, 3 and 4. Now what you need to do? Forward backward allocation. Now you need to understand this procedure. Okay. The name of this particular procedure is defined as a forward backward. Now, so name itself suggests that I need to go start with moving forward, and if at all I need to go backward, then I can go for a backward. But always whenever I am moving, moving has to be go through a diagonally manner. So whenever I move, I will move in a diagonally manner only. Okay. So I will go either forward. So my priority is always go to forward. Okay. But if there could be a chance that I cannot move forward, then I need to go to a backward. Okay. So at what time I need to go to a backward, that I will explain. Okay. But what you need to understand that you need to move forward if possible, and if forward movement is not possible, then you need to go for a backward. Okay. It is something like that you are going in a road, means I go with that you have to go straight. So sometimes you go that you will go straight, then there is a one turn is there, that but there is that turn is always you need to go to left, there is no right turn. Okay. So you need to go to a left, Of course, okay, so you are moving, but moving in the same direction only. Okay, that you are moving forward, but when you go straight, then you observe that there is a means obstacle. So now you cannot move forward, but then you will take a left only because that is the only path which exists to you. So similarly over here, that whenever you move forward, then you go forward, and if forward part is not available, then you need to think about the other alternative, which is a backward. Okay, so that means you need to go to forward and then you need to go to a backward. Now, if forward backward allocation, I will always draw a three column R1, R2 and R3. So this R1, R2, R3 is that. Apart from that, before that you need to put input and you need to put output. Okay, so this is a standard procedure that you need to follow. Okay, so number of column will be always the minimum number of register that you need to take care. And then apart from that, you need to also define your input as well as your output. So R1, R2, R3, and then you have an input, you have an output. Now always you will start moving from input towards the output. Okay, so what is your starting point? As I said that you need to move forward. Okay, always if part is possible, then you need to move forward only. If part is not possible, then you need to think about the backward. But what is your starting point? Starting point is you need to start with the input and then you need to reach towards your output. Now, if you think about this, then you are starting with A. Now, A is for a 1, 2, 3, 4 clock cycle. Okay, so when I say first clock cycle, that means I need to start with the time instance 0. So from 0, A is started. Now, for A, I need to move forward. Up to how much I need to move? Until the life of A exists. So life of A exists from 1 to 4. Okay, so I am starting with this. So this is my first clock cycle for A. I am moving forward. Again, in a second clock cycle, I am moving forward. So I am moving diagonally. Just observe that this part I am following is a diagonally. Okay, so A is moving in a diagonally manner. So first clock cycle, second clock cycle, third clock cycle. Now here there is output. There is no next register available. Here there is no next register available. Okay, so this forward backward allocation always exists for a register. Please don't be confused. Okay, so ये register के लिए ही applicable है. So I am moving from input. Of course, the starting point is input. Okay, and once your journey is completed, then you consider that journey is your destination and you will consider that as the output. But still, the journey is from 1 to 4. Okay, so for a forward allocation, I will go for a diagonally first clock cycle, second clock cycle, third clock cycle, and here there is no next way I can move forward. Okay, so actually this arrow is wrongly actually being defined, but here at R3, after that there is no R4, so that means you need to go backward now. So from R3 you need to go to R2, whether this particular space remain blank or not, that you need to find it out. If this space, see, always the part is you need to go to R1 to R2 to R3. So that is your forward part. And when I say backward, then backward is R3 to R2 and R1. Okay, that means R3, from R3 you need to go to R2 only, and from R2 you need to go to R1. You cannot go from R3 to R1 direct. You can go R3 to R1 direct only and only when this R2 at that particular moment is not free. Okay, so over here I am moving forward A 1, 2, 3. Then still the life of A is there because life of A is there till 4 clock cycle. So that means I will now complete the backward allocation now at this particular moment. You just observe there is a round bracket. Now the round bracket suggests that now A has completed its journey. The life of A was 1 to 4 clock cycle, and I have made the journey from 1, 2, 3 and 4 clock cycle. Of course 1, 2, 3 clock cycle I am moving forward, but since when I move from third to fourth clock cycle, there is no forward journey is possible. Then I need to go to a backward. So that's why from R3 I go for a R2, and this is the end of the journey. So means A life is completed because A was exist from 1 to 4. So once the life of particular variable completed at that particular instance, you need to take it as a output. तो यहाँ पे ए की जर्नी खत्म हो गई जिसकी वजह से मैंने ए को आउट में ले लिया. ठीक है. नाउ जस्ट थिंक अबाउट बी. सो आई एम जस्ट रिमूविंग इट सो दैट it would be easier to understand. Okay, now think about life of B. Now B life, we know that B life exists from 2 to 7. Okay, so that means B, this is my nothing but this is my first clock cycle, this is my second clock cycle. That means this is my second clock cycle, this is my third clock cycle. Again I am moving diagonally. Please ensure that diagonally you need to move and you need to increase your clock period. So diagonally you are moving. Okay, so 2, 3, then 4. Again when you reach up to 4, then you observe that there is a dead end for a number of register. So then you need to go to at 5, you need to go to B. Now again, if you observe that after 5, for a 6, I am moving forward. Okay. See, always the priority is to move forward. But if that is not possible, I need to go to backward. But if you observe that from 4, then 4 to 5, I am going backward. But once I go for a 5 backward, then now I see that there is an opportunity now from at a 6 clock cycle to moving again forward. Okay. So at a 6 clock cycle, I am moving forward, and for a 7 clock cycle, as I cannot move beyond R3, now I need to go to backward. Now life of B is 2 to 7. So that is being considered 2, 3, 4, 5, 6, 7. Now life of B is completed. So B is being taken out over here. Similarly, I need to apply for C. Now C life is applicable for 5, 6, 7. So that means C will go to 5 in diagonally 5, 6, 7. Now for C, I think there is no need to go for any backward because 5, 6, 7. So that 3 instances there where 3 register can occupy that value. So that C life is completed. So I will make it this as a out. Okay. So this way you can go for a forward and backward allocation. Now I just stop at this particular point and I leave it to you just to realize that how this table is being prepared, because this circuit, which is your folded architecture, that totally depends upon how efficiently or how accurately you have designed your forward backward allocation table. So this folding structure for a register I will discuss next time. But before that, you need to understand this forward backward allocation. This table is very important. Okay. So I just request you to go through this. This again I am mentioning chapter 6 of your KK Parhi folding. You just try to go through it, and if at all any issue, then we can meet. Now another thing is, from next week I believe that we can now conduct the offline class. So maybe at VLTC, whatever the schedule slot is there, and at that schedule slot, whatever the physical location is there, over there we can meet. There is no problem. Okay. So at that time, maybe as I announced that if you have any doubt, whatever we have discussed this week, then maybe physically I can solve at that particular time. Okay. So if you have any doubt for today, then I will be more than happy to answer. Otherwise, we can end up our session for today. Yes. Okay. So with this, we are ending up our session. Okay. Is there anything? Please share retiming PDF. Means that retiming, I think it was there. Oh, if you want, I think it should be there. For a retiming, probably I have used the board only. That PPT is there, but I think I'm not sure that whether I have not shared or not. But if it is not shared, then I will again share it. Okay. And I will share this PPT also with you. Okay.
Okay, sir.
Okay. Okay. Thank you.